Welcome to the computer lab on multiple state models. So together with Bavo and Sander de Vriend, I prepared an R implementation of the concepts that we encountered in the chapters discussing the multiple state models and the calculations within such multi-state models. So first of all, where can you find the material? So our material is available on this GitHub repository, so you can find there the lecture sheets. You can also find there an R script that actually contains all the code chunks that you will encounter throughout this presentation, right? Here are our coordinates, so you know that by now. You need a fairly recent version of R, and preferably also RStudio to make sure that you can run these instructions. The good thing perhaps is that we don't rely on any R packages. So all the instructions that we're going to use now, they're just built in, or they are functions that we're going to implement ourselves. So it's a fairly easy session from that perspective. So here are our learning outcomes, the goals for today's workshop. So what do we essentially want to do? We want to numerically evaluate the concepts we discussed in the course so far and gain some intuition, gain a bit of a feeling about these concepts to make sure that we understand how they work and make sure that we can translate the formulas from the book to an actual implementation and to a numerical result. We're going to focus on three things: transition probabilities, premium calculations, and policy values. And an illustration of each of them brings you then the essential stuff that you need to know. Then you can do all kinds of additional exercises using the code that I will discuss today, and just making adjustments based on the kind of multi-state model that you want to use, the type of product that you want to value, etc., etc. Yeah. So what are the challenges around? It's going to be about numerical integration. So maybe you've encountered that already in other courses or for other projects, but I'm going to show you, in fact, 3 different ways to do the numerical integration and show you that the results, at least for the kind of integrals that we're going to look at here, are close to each other. That's the first concept. And then another concept is, how about working with this set of differential equations? Yeah, we encountered already this Euler method or Euler scheme in the theory. So we're going to put that together in R and use it to value the policies, to calculate the policy values related to our multi-state models. That's what we want to do. All right, so here we go. I'm going to start with the first example on transition probabilities. So here's the example. That was example 8.4 from our book. And we're going to start with the permanent disability model. So that's an easy setup where we can make a transition from state 0 to state 1, from 0 to 2, and from 1 to 2. And given are the transition intensities that come with those allowed transitions, so to say. And then we remember from the exercise in the book, the whole idea is, of course, at first, to be able to calculate transition probabilities. For instance, what is the probability for a 60-year-old to make the transition from 0 to 1, from the healthy state to the disabled state, in a period of 10 years from now. So how would we do that? Well, first of all, I'm going to write down the theoretical expression for this transition probability. That's going to be very fast because we already spent time on explaining that setup. And then we're going to switch to R and actually do the numerical calculation ourselves. So here we go. First of all, if we look at this permanent disability model, then we can look at the sojourn probabilities and the probability to stay in state 0, the healthy state, during a period of t years. And then we remember from the course that that's the exponential function of minus the integrated total force of decrement, if you want, that is applicable to somebody in the healthy state. So that's the sum of the force of transition or the transition intensity to go from 0 to 1 and to go from 0 to 2. Now, in fact, if you plug in here the expressions which are given for the transition intensities, then it turns out that you can do that integral yourself. So I just copy here the solution. So I can do that analytically. There is no need to rely on a numerical technique for that. Okay, so that's the first thing. If I then look at the sojourn probability, the probability to stay in the disabled state, that is then along the same kind of thinking. That's the exponential of minus the integrated transition intensity to go from state 1 to state 2. And again, that's an integral I can work out myself. You see the solution printed over here. So nothing new so far. That's material that we already discussed on the lecture sheets. Now, if we put these things together, we can get an expression for the requested probability. And that was the probability for a 60-year-old to make the transition to start in the healthy state at time 0 and to be in the disabled state in 10 years from now, right? So what does that mean? We can put this probability together as follows. So it means that you're going to stay in the healthy state until a certain age, 60 plus t. Then you're going to make the transition into the disabled state. And then for the remainder of the considered time interval, so that's the duration of 10 minus t, you're going to stay in this disabled state. And you want the t to run from 0 to 10. So that's a way how we can write down this probability. And once again, we can only do that here with such a simple expression because we're working in a multi-state model where transitions up and back are not possible. It's the permanent disability model. Now, of course, if I would plug in this expression here on top of my sheet, if I would plug in this expression and plug in the expression for the transition intensity, I get something that I can no longer handle myself with pen and paper. So I want to put this together in R, do the numerical integration, and get some numerical results for this probability. That's the idea. That's my mission so far. So here we go. And yeah, once again, my intention here is just to guide you through the essential building blocks of this code, but nothing is really spectacular, right? So I think I can briefly touch upon the main concepts, and then I guess you can figure out the rest of the syntax or the rest of the details. So first of all, how did I put it together? We defined some constants, particularly the constants which are used in the specification of the transition intensities, because they're given here. Of course, that's a bit of an artificial situation. In our book, we take the transition intensities as given. In reality, this is what you would have to estimate from a given data set with the observed number of transitions over a certain time period on a group of insureds who bought this particular insurance product that we are discussing. Yeah. So assume the constants to be given. What did I do next? I wrote a function to specify the sojourn probability, the probability to stay in the healthy state. And you see I give a couple of arguments here. So I give my t, the number of years I want to stay in the healthy state, the age that I consider. So here that would be a 60-year-old. And then I pass along these constants to be used. What this function does, it's nothing but the implementation that you saw, or the specification that you saw of the integral that I calculated manually on the previous sheet. If I evaluate this thing, if I call this function and I say, okay, give me the 10-year probability of staying in the healthy state for a 60-year-old and for the given values of my constants, then I get a probability of 58%, which is exactly what you will also see in the book if you would compare these values. So we do the same for the probability to stay in the disabled state, exactly the same kind of thinking, put everything in a function, let it be, or let this function take as arguments the t, the duration considered, and the age from which you start. And then I'll do a check. So I calculate the 10-year probability of staying in the disabled state. and I get here this outcome of almost 80%. So again, this should match the answer that you find in the book. My final function, which I need, my third building block, is a transition intensity to go from 0 to 1 at a specific age, right? So that's just the given functional form for this transition intensity. Putting that all together, what do I get? I want to write down the function which I would like to integrate. And that's this function that combines the three building blocks that we encountered before. So the probability to stay in the healthy state, then the transition intensity to go from the healthy to the disabled state, and then the probability to stay in the disabled state. So if I put that together, I'm going to use these three building blocks. You recognize them here. And I put them together in the appropriate way. I multiply them. That's how I put together the function of which I need to numerically calculate the integral. So do note that we have a couple of arguments here. We have t, we have h, and we have what I called end, the end period I wish to consider. So age is obvious. We're going to consider here a 60-year-old. The end, that means I'm going to look at my 10-year period. So the value for end in the calculation that I want to do will be the 10-year, right? And then the t is going to run from this from 0 to the value of end, right? So that's how I put together the specification here. So you see here I start from calculating the sojourn probability, the probability to stay in the healthy state for another t years. Then I take the transition intensity, you make the move at h plus t, and then for the remainder of the period and minus t, you stay in the disabled state. And at that time, or at the start of your episode of disability, you have an h plus t. That's the idea. Now, of course, what do we want to do? We want to numerically evaluate this integral. We're going to do that, first of all, with the built-in function integrate. We're going to pass on the function that we wish to integrate, and we're going to specify the lower and the upper bounds of our integral, right? So in this case, if you run this instruction, the function I wish to integrate is the one I put together over here. I want to go from 0 to 10. I give as the age 60, and as this end, I give again the 10-year period. I specify my constants, and I find here below the numerically evaluated probability. What else can we say about this? Well, the numerical technique that R is using under the hood, if you call this function integrate, it's yeah, let's say that by default it's slightly different from the methods that the authors of our book propose. So what I do on the next sheet is I'm also going to manually put this integration methods considered in the appendix of the Dixon et al. Book. I'm also going to put those together and make the comparison with the results that I obtain over here. Yeah, but this would be a perfect strategy to actually do the calculation we need to have. If you prefer to put that all together in a single function, if you say I don't like all these different building blocks which Catherine put together, so here I do it once again, where I create, let's say, a big function where I put everything together, and where I will then ask, okay, let's now do the integral of this function over here between 0 and 10. Yeah, so it's a slightly different way of putting it together. It's just what you prefer as a style to put this together. So just a slight word about these numerical integration techniques, and this is something I do not consider you to be aware of. So I mean, this is not something I'm going to ask in the exam, or whatever. The idea is that you just can make sense out of the kind of R code that I'm showing here. But I'm not going to ask you to motivate where this trapezium rule or the Simpson rule or whatever is coming from, right? So this is something we'll just take as a given for this course. So why do I mention that here? Because if you look at Appendix B from the book, there the authors focus on the numerical evaluation of an integral like this for a certain function f between and over an interval a to b. And then the authors of the book propose either the trapezium rule to do this. So they define then a step size h, let's say that's b minus a divided by a certain n. And then they explain, okay, then your integral can be approximated by the value that you see over here. Sorry for putting the point or the dot in such a strange way. That was not meant to be. So that's what my trapezium rule would do. If you rely on the Simpson rule, you're going to use a step size h, which will be b minus a divided by 2 times n, or the number of grid points n for a given step size a, h would be considered like this. And then the Simpson rule puts or approximates the integral with the expression that you see over here. Yeah, so that is what the authors of the book put forward as their way to do numerical integration. So the only thing I want to show you here is that if we put these implementations together, how does that impact our results, or how close are our results with the value from the built-in integrate function from R that we already obtained. How are we going to do that? Here is again the transition probability that I wish to consider. This is my integral from 0 to 10. You know the building blocks by now. This is what we need to work with. So what I first of all did is I specified a grid that I'm going to use. And this grid is using a step size of 1 over 12. That's inspired by what the authors of the book propose. You can play with that, of course, to check how that influences your results, but it's not something I want to spend time on here. So what are we going to do? We put the boundaries. A0, B is 10, or H is 60. We put a grid together that goes from A to B in steps of size H, and N grid is then the length, the number of points in our grid. So what are we going to do? We're going to evaluate the function f in the different points along our grid. So this is something I highlight the essential parts over here, but you're going to start with H60, and you're going to evaluate the P00 function in the grid points. You're going to multiply then with the transition intensity to go from 0 to 1 along the edges that you get by evaluating this H plus grid. And do remember, grid is a vector which runs from 0 to 10 in steps of size 1 over 12. So what I do here is I start with H60, then I do H60 plus 1 over 12, and so on and so forth, and I end with, it's going to be H70, right? And here I then focus on the third building block over here. So here I start at H plus grid, and then I consider the end period. That's my 10 minus my grid points. That's how I move on with this sojourn probability. Okay. With the trapezium rule, I then code the instruction that was given on the previous sheet. And I find here the numerical evaluation of my transition probability using this trapezium rule. Here I do the same with the Simpson rule. And you see that these results are close. They also match the results that are reported in the book. And if we go back to the result that we found with the built-in integration function, then we're here. So also here you see that all these results actually match up to a certain number of digits. All right. So that's what I wanted to discuss in terms of numerically evaluating a transition probability. So just to show you that we can actually do this, you could also do this in Excel or in another tool. But I always like to be convinced that the values reported in the book, that I indeed can reproduce them. So that was the idea of this first illustration. Good, let's move on. Now we've got another example to cover. I'm gonna continue with my transition probabilities, but I'm gonna switch to a more complex multi-state model. So here I've got the disability income model, where I've got transitions from 0 to 1, 0 to 2, from 1 to 0, from 1 to 2, and I guess I mentioned all of them. So the difference with the previous setting, as you know, is that now our policyholders can go up and back between state 0 and 1. And this should also ring a bell that the calculation of transition probabilities then becomes more complicated, because you have to take into account that these transitions up and back are possible. So let's see how we can do that. Let's see how we can calculate probabilities of this type. You could come up with other illustrations as well, but that's the idea. Again, our transition intensities are given. So we've got the functional expressions over here. We get values for the constants and so on and so forth. So let's go. And first of all, as we discussed in the lectures, we're now going to rely on these Kolmogorov equations to do the evaluation of the transition probabilities. So I copied again the Kolmogorov forward equations as we derived them in the class. And I'm going to rewrite this differential equation by saying, okay, that should be approximately then be equal to the following recursive relation, right? So that's an approximation, but something I can work with in an environment like R or like Excel to actually come up with a numerical evaluation of my transition probability. So I think the main takeaway here is that you see the difference between, okay, here I really need to go for the Kolmogorov approach and look at this recursive scheme over here, whereas in the previous example, the multi-state model was rather simple, and I could immediately write down the integral expression for each of the transition probabilities that I was interested in. And then the job was just to go from the integral on paper to a numerical evaluation of this integral. So here I'm going to work in a slightly different way. I look at this set of differential equations, and of course the first thing I need to do is to match the general form of my Kolmogorov set of equations to the actual application I want to consider with the given multi-state model, in this case the disability income model. Okay, so for our particular application, I write down which intensities are different from 0, which terms drop from the expression, and so on. So I get this kind of starting point, let's say. And I want to make sense out of this in a numerical way. Good. So nothing new here. All of that was discussed in class, but this is what we need in order to move forward. So how we're going to do that? Here's what I put together. Nothing spectacular here. It's just a matter of writing the appropriate function and then moving in a recursive way. So with a loop through these functions. So first of all, we define the transition intensities. Perhaps I already did that, or perhaps they're similar. Yeah, I guess they correspond to the ones we already had in the first example. But just to be sure, I re-specified all of them. We then write down a function to evaluate the right-hand side of the expressions on the previous sheet. So that essentially means that I'm going to put a function together to get the right-hand side over here. Yeah, dropping, of course, the little o of h. So what I get here is, as arguments, the TP00, the TP01, the step size h, and the hx. And I'm going to say, yeah, if I need to evaluate that function or that expression that I see on the right-hand side, I get something like this. So you can match these expressions and you will see that these are the same. And I do the same for the THP01, which is then the right-hand side of the second equation over here. So putting that all together, I now got my functions, which I want to use, and then the idea is just to use them in the appropriate way. That's essentially what I wish to do. So I can start easily. I can say let's use these functions to evaluate the TP6000 for t equal to 1/12. And assuming that I start from the following boundary conditions. And these boundary conditions, they make sense, of course, if you are 60 years old and we consider the sojourn probability. Sorry, that was wrong. So if you are 60 years old and you start in the healthy state, then what is the probability that in 0 years from now you will be in the healthy state? That probability is 1, because you were in the healthy state, right? So you stay there. And then the other way around, if we look at a 60-year-old who starts in the healthy state at age 60, what's the probability that in 0 years from now he will be in the disabled state? Yeah, that's impossible because there is no time to make the move, so that probability is 0. So these are our boundary conditions, and now we can move from t equals 0 to t equal 1/12 using the expression that you see over here, right? So using this function call. So what do? I give as the arguments TP00, that's 1, TP01, that's 0, my h is 1/12, and my x, my starting age, is 60. I evaluate this probability, and you see that I exactly get the value reported in the book. I can do the same for the probability to go from the healthy state to the disabled state in a period of length 1 month, right? So exactly the same kind of arguments. I call the second function over here, and I indeed get the value reported in the book. So that seems to work, right? Putting it all together, I now, of course, want to do this repetitively so that I can say, well, in 10 years from now, what is the probability, etc., etc. So that's what you see on the next sheet. Here we put it together with a for loop. There are people who would do it differently, of course, but I think this is the most intuitive way to get some grip with the code and with the implementation. So I start from my where do I start? I start from my boundary conditions, which you see over here. Yeah. And I'm gonna go then with steps of length 1/12, starting from these boundary conditions, and then by repetitively calling the functions that I just introduced. So that's essentially what you see over here. So moving from these boundary conditions, I'm gonna go then to the results. So I call this the matrix results with 2 columns, and the first probability here is going to be the P00. The second probability here is going to be the P01. Start from these boundary conditions. Then on the next line, I report the probabilities to I report the corresponding probabilities evaluated in a period of 1/12, and so on and so forth. Yeah. Yeah, I was a little bit confused by the entries in the first line, but you see that I evaluate them over here by actually putting the h equal to 0. So by putting the length of the transition period equal to 0. And then you see that you indeed get the 1 and the 0. And then from there on, we move the results at position I plus 1 in my matrix can be obtained from the results in the preceding row by using my function calls in the appropriate way. You see that over here, I always use the step size 1/12, and I let my age, of course, change. I let my age move along these values in the grid. So putting that all together, I can in the end evaluate what's the probability in a 10-year period. So then we're here in a 10-year period to be again in the healthy state or to be in the disabled state. So these values should match the ones which are reported in the book. In fact, we completely reproduced table 8.1 in the book. So where you see the grid points T, where you see the values for the transition intensities evaluated in these grid points, and where you then can find our transition probabilities. Yeah, so if you put that next to the table from the book, you should see that that nicely matches our results. Right. And we redo here an example that we discussed also during the theory classes. So we have a 10-year disability income product, which is issued to a healthy 60-year-old. We've got an interest rate of 5% per year, and we want to value the following product. So premiums are payable continuously in the healthy state. There's a benefit of 20,000 euro per year payable continuously in the disabled state. And there is a death benefit of 50,000 euro upon the transition from the healthy or the disabled state into the dead state. So I want to calculate what is the annual premium rate. Let's call that P. So how would we do this? Okay. So let's get started. First of all, there are some constants we want to initialize. What is given is the interest rate is 5% per year. Yeah, so that's in a discrete kind of thinking. So that's the I, the rate per year, that's 5%. I'm going to translate that into a force of interest, the delta, by using the connection that 1 plus I is e to the power delta, yeah, such that delta is then the logarithm of 1 plus I. The reason I do that is because I need to value this product in a continuous way, because it's given that premiums are payable continuously, the disability benefit is paid continuously, and so on and so forth. So I need to work in a continuous time setting. So I need the force of interest. I define my step size, again, 1/12. I'm going to run here over a 10-year period. The reason for that is that it's a 10-year disability income product. So I specify my lower and upper band. I calculate the number of grid points in the Simpson rule that is corresponding to this step size H that I defined. And I specify a grid from 0 to 10 in steps of size 1/12. And I calculate the length of this grid. So what I'm going to do is I'm going to work in a vectorized sense. So I'm going to evaluate the concepts that I need over the points in my grid, over the time points in my grid. And then I can use, for example, the trapezium or the Simpson rule to do numerical evaluation of my integrals. So first of all, let me look at the discounting factors. So the discounting factors, that's e to the power minus delta times t, right? But the time points t that I wish to consider are those points which are stored in my grid. So that's 0, 1/12, 2/12, and so on and so forth. So using the vectorized way of thinking of R, I can get my grid with discount factors by just doing this vectorized calculation. What I'm going to do here is a little bit special, perhaps, but I'm going to extract. So I'm going to, really extract the variables, which I had in the table 8.1, which I calculated in the previous example. I'm going to extract those variables such that I can actually call the variables here and their values and use their values in the calculations over here. Yeah, so that's a bit of a technical detail, just to quickly get the transition intensities and also these transition probabilities, which I calculated in the previous example. I want to recycle what I did in this previous example. So here we go. This is our EPV for the premiums. It's a continuous time calculation. It's an annuity type of calculation. So I have an integral from 0 to 10, e to the power minus delta t, and then this transition probability TP6000, right? And I know that I'm in the disability income model, so I need the TP00s, which I calculated in this table 8.1 earlier on. P is my annual premium rate. I want to calculate this one. I understand what this means, and in the book, a value was reported like this. So in the book, they say that the numerical value or the numerical evaluation of this integral here for the annuity would be 6.5714. And of course, we want to check this with R. Is this true? Is this correct? So what do? Once again, I'm calculating with vectors. So this is my vector of discount factors along this grid with step size 1/12 that I constructed. And the THP00, that's what I got from my table, right? That's this vector with the values of this transition probability evaluated along the grid points that I created. So if I multiply these two in an element-wise way, then I get exactly what I need over here in the integral. And having this vector, I can then apply the trapezium rule or the Simpson rule. So that's exactly the same kind of code as we discussed earlier on. And I retrieve here the numerical value for this integral. And I indeed see, okay, what the authors of the book report, that is correct. Yeah. Does that make sense? So that's in a nutshell what I do. I sort of vectorize this function, calculate the values along a fine grid, and then I do, in this case, either the trapezium rule or the Simpson rule to do the numerical evaluation. So the valuation of the sickness benefits is, of course, pretty similar, but now I need to work with the transition probabilities TP6001. So I get these along the same kind of thinking as for the valuation of the premiums. I do the element-wise multiplication of the discount factors with my transition probabilities. I use my trapezium rule or Simpson rule, and I find the following value. And here on the left, I show the value that was reported in the book. So, okay, that's also correct. So we can reproduce this result. The last building block is the EPV of the death benefit. So that's slightly different. So here we see that the debt benefit is 50,000 euro, which is payable upon transition into the debt state. You can make this transition from state 0 to state 2, or from state 1 to state 2, right? And we're going to issue this product to a healthy policyholder at time 0. So we're going to start in state 0. So if I write down the integral expression for the EPV of the debt benefit, I get something like this. Once again, the value is reported in the book. We want to check this, so we put together the function that we numerically want to integrate, the function over here. And we're going to do that by evaluating this function over our grid. So that's what you recognize over here. I've got my discount factors, I got my TP00, I got my intensity mu02, I got the TP01 and the intensity mu12. This is all extracted from my reproduction of this table 8.1 in the previous example. I do my trapezium rule, or I do my Simpson rule, and I see that, okay, what Dixon, Hardy, and Walters report in the book, that does make sense. That's the same result as what we obtain over here. Putting it all together, I can write down my actuarial equivalence. I can solve for P, and that's the final step that you see over here. Which allows you to retrieve the value for P that is also reported in the book. Okay. So in fact, taken from a computational point of view, there is nothing new here. We just rely on the numerical evaluation of certain integrals. Once again, we just need to put these integrals together in the correct way and then do the numerical evaluation. And we do that here with the trapezium or the Simpson rule, just to be close to the kind of thinking that the other authors of the book propose in the textbook. Yeah, you can also do that with the integrate function in R, but I just wanted to be close to the kind of thinking discussed in the book. All right, so the last thing we want to do is about policy evaluation. And we know that there's this thing called the Thiele differential equations, which we want to use to do the evaluation of our policy values over time in a multi-state setting. So we're going to put that here together. We start with the disability income model, pictured here on the right. We've got a 40-year-old policyholder. We've got a duration of 20 years, a force of interest of 4%, a certain sickness benefit, yeah, disability benefit B, if I'm not mistaken, and a lump sum S to be paid on that, if I remember well. We've got our transition intensities, and the goal is now to calculate our policy values. We want to calculate our policy values at certain time points, given that the duration of our product is 20 years. Yeah, so it's a term insurance product with a duration of 20 years. And we also want to do the evaluation for a given value of the premium, of the annual premium rate. Okay, so let's start from there. So you know that the trick to do the numerical evaluation here is the Thiele differential equation. And this Thiele differential equation, you see it over here. So we know that the policy value in a multi-state model is state specific. Now, so we've got one expression for VI for each state I in the model. And we know that we have to solve these equations all together in order to get a grip on the evolution of our policy values. Yeah. So the first thing we need to do is to go from this general expression to the specific context, to the specific application that we want to discuss. So that's, for our case, we have premiums paid continuously, we've got sickness benefits paid continuously, and we've got our lump sum S when you make the transition from the zero state or the disability state into the death state. Yeah. So of course, I do some rewriting here. I do two things here. I go from the differential equation to like an approximate format. And I also plug in the specific settings, the specific transition intensities, the specific B and S and so on for the application that I have in mind. If you look at this thing, you see that I wrote the recursion here in a backwards way. So we're going to start from the endpoint and we're going to go backwards. And that's the most easy thing to do here because you've got a term insurance product. And you know that at the end of the term, the policy value in each state should be 0. So then you can work backwards and get the policy values in other time points, so to say. So that's the setting that we're going to do here. I cannot do it differently here because, or not at first sight, because I don't know what the policy value would be at time 0. Because I didn't, normally you would say, okay, if the premium is calculated via actuarial equivalence, then the policy value at time 0 would be 0, and then you can go from there. But here, I'm not working with the actuarially equivalent premium. I'm working with a given premium, of which I'm not sure it's the actuarially equivalent premium. So that's why I'm going to go backwards. Good. So first thing we do is we specify the constants we need. And now you have to be a little bit careful here because we're going to go backwards. But if I implement it in R, I start with my boundary conditions at the end of the term. I put those as the first entry in my vector that's going to describe the evolution of the policy value over time. Yeah, so I'm going to go with the policy value at time n equal to 20 years. And that's what I put as first entries in my vector. That's the way how I did it. So here we go with specifying these boundary conditions. That's the TV0, that's the TV1. They're both 0 at the end of the term. And my step size is 1/12, right? I've got some constants here, and I've got the specification of my transition intensities. And I now want to know, how can I go to policy values at different time points t? Now, namely, t is 10 and t is 0 are requested in the book. Yeah. So once again, I'm going to work with my step size. I'm going to divide a 10-year period in 120 steps. So that means a 20-year period in 240 steps. And I'm going to do this backwards reasoning. So here we go. So what you see here is I've got the for loop that describes in a recursive way my Thiele differential equations approached with this Euler method that we discussed in the class. So that's essentially the expression that you saw there on the sheet earlier on. Yeah, so I just want to say the loop is moving forward. It's going to go from I to I plus 1, but the thinking is a backwards thinking. So maybe that's a little bit different than usual, but that's how we put it together. So what you recognize here is you use the age. You have to be careful here with the age in which you're going to evaluate your intensity. So that's here x plus n. X is 40 years, n is 20 years, and then you're going to move backwards and so on. Yeah. So we start with the first entries in my vector being 0. These are the policy values at the end of the term. And ultimately, if I plug in P is 5,500, if I plug in the given value for B, for S, for the transition intensities and so on, then I retrieve here the policy value at time 10 years, and I retrieve the policy value at time 0. And these are the values which indeed match what was reported in the book. So these are my policy values moving over time, starting from given boundary conditions, which in this case are the policy values at the end of the term. So that was the calculation for P is 5,500. In the book, if you remember, we also did the calculation then for P equals 6,000. There you found a negative policy value at time 0. And then we applied this approximation where we said, okay, now let's assume that the policy value at time 0 is linearly depending on the P. And let's do this linear approximation to figure out what the actuarially equivalent premium P would be. That is the premium P that forces the policy value at time 0 to be 0. Yeah. That kind of thinking, we formalized it over here as well. So what we're going to do is we're going to search the equivalence premium P, for which the policy value at time 0 for in state 0 is equal to 0. So what I did here is I created the previous expression, but I'm now considering this to be a function of P. Yeah, and with this decades, I mean that we have, a decade is 10 years. I'm working here with periods of 10 years. So I have a duration here of 20 years. So that's what why I put decades equal to 2. And I'm going to consider this to be a function of an unknown P. And actually what I'm going to do is I'm going to search for the P that makes this I need to explain one step. So I've got the same sequence here, the same backwards kind of reasoning. But what I return here then is the policy value in state 0 at time 0, right? And that's coded here with 120 times 2 plus 1, which is the same as what you had over here. That's my policy value at time 0 if I reason along the grid that I specified over here. So what I'm going to do is this function gives me back the policy value for state 0 at time 0, and it's relying on an unknown P. And what I then do is I call the function uniroot to say, okay, calculate or find me the premium P that makes this function equal to 0. So that would give me then the actuarially equivalent premium. I specify here the range of values, possible values for P where my function can look, because I already have some insights based on the calculations I did with 5,500 and 6,000, that I saw that I went from a positive value for this 0v0 to a negative value. So I say, okay, let's look for the actuarially equivalent premium between or along this interval of values for P that we already considered. So here is my actuarial equivalent premium, and that's in fact very, very close to the one that we obtained a couple of lectures ago when we did this linear interpolation or linear approximation kind of thinking. Yeah, so that's what I wanted to illustrate here as well.